Okay, section 7.3. We are adding and subtracting rational expressions with common denominators, and we're also going to be finding the LCD. Now, adding rational expressions is nothing but adding fractions. So the rule is that you cannot even add or subtract fractions or rational expressions unless they have the same denominators. And in the case of them having the same denominator, all you do is, when the denominators are the same, you write your answer with that same common denominator, and you just add or subtract the numerators according to the operation that's given. Then you reduce it. So in this example, we have the first example, we're going to have 6/5 plus 2/5. Well, since the denominators are the same, we're going to come up with 8/5. Okay? And 8/5 cannot be reduced. There's no need to write it as a mixed number. Just leave it like that. Okay? But the same thing is true when you are adding, as in this second example. The first thing you want to do is identify what operation are you performing. And here you're performing addition, so the denominators are the same, which is a good thing. So all we have to do to add the two fractions is keep the denominator the same, x plus 2, and add the numerators. 9 plus 3 is 12. Well, if that was subtraction, we would have subtracted as well. Then we would simplify the fraction or the rational expression by factoring the numerator and denominator and canceling whatever they have in common. But in this case, there's nothing in common. So the rule here is to add or subtract rational expressions with common denominators. If P over R and Q over R are rational expressions, then we add or subtract the numerators and place the sum or difference over the common denominator. And then you would simplify if necessary. Okay? So let's look at this example. Here we have 7a over 4b plus a over 4b. First thing to recognize is that it's addition and the denominators are the same. So the new answer, your answer, will have a denominator of 4b, and we have 7a plus 1a, okay? That gives you 8a. But look at the 8 and the 4. The 8 over 4 can be reduced, okay? So 4 divides 4 one time. 4 divides 8 two times. So ultimately, we have a sum of 2a over b. Next example, we have 8x plus 8x over 3y plus x over 3y. We get as a sum 9x over 3y. Once again, this can be simplified because 3 divides 3 one time, 3 divides 9 three times. So we have now 3x over y. Next example, this is a subtraction problem, but the denominators are the same. These are the kinds of things that you have to think about. It's subtraction, the denominators are the same, so I can just go ahead and place everything in my answer over 3x minus 2, and then I'll just subtract the numerators. There's a 3x minus 2. Now notice what happens here. 3x minus 2 in the numerator and 3x minus 2 in the denominator are each binomials. They are two-term polynomials. It's not a 3x over 3x and a negative 2 over a negative 2. That is not what it is. So you have to treat them, both of these binomials, as if they are a married couple. You cannot cancel a 3x with a 3x, okay? And a negative 2 with a negative 2. If you're going to cancel, you have to cancel the whole expression with the other whole expression, okay? And that's what we have to do. Please be very, very careful. You cannot cancel terms within a polynomial with another term in another polynomial. You either have to factor something out and cancel it or cancel the whole thing. So ultimately, this answer is going to be 1. Similarly, here we have 2x minus 5 is the common denominator. And then we get the subtraction of 2x minus 5 in the numerator. So that simplifies to 1. Because 2x minus 5 divided by 2x minus 5. Remember, anything divided by itself is 1, except 0 divided by 0. We don't do that. Now, let's subtract. First things first, let's recognize that we have a subtraction problem and the denominators are the same. So, let's see what we get. We have whatever we're going to have all over x plus 3. Let's write out the first numerator, which is 4x squared plus 15x. But watch what happens now. Because we are subtracting a whole binomial, we must be careful to change the sign. Okay? We must be careful to change the sign of everything. So I'm going to write it like this, just so you can see it. We're subtracting the whole binomial of 8x plus 15. We're not just subtracting the 8x, we're subtracting the 15 as well. Notice how I wrote it here, okay? I wrote it with the subtraction and then parentheses around the 8x plus 15. Okay, after you've done this for a few times, you won't have to necessarily do that, but please be careful that you do. Make sure you subtract the whole thing. That's a big mistake that students make. So now I'm just going to rewrite it as minus 8x minus 15 all over x plus 3. And then that will then allow me to combine like terms in the numerator. Okay? So in the numerator, we have 4x squared. 15x minus 8x is what? 7x minus 15 all over x plus 3. Okay, and if we factor 4x squared plus 7x minus 15, we get, now you have to go off to the side and factor this using the grouping method. We get x plus 3 times 4x minus 5 all over x plus 3. And you can see now where x plus 3 cancels with an x plus 3, they become 1s, which now leaves us with 4x minus 5 as our solution. Now, you have to be very careful that, see this little hint right here? It says, notice how the numerator, well, of course, in our case, our numerator is this numerator that they're talking about here. is being subtracted. 8x plus 15 is being subtracted. So you have to apply these parentheses in order to change the sign for everything. So be very, very careful with subtraction. I'm going to do another problem. Same thing. Okay? It's a subtraction problem. I'm going to go through it. The denominators are the same. So we're going to have x plus 2 as a denominator. Then we're going to have 2x squared plus 5x minus the whole binomial 4x plus 6. Okay? That's the biggest mistake students make. So then we have 2x squared plus 5x minus 4x minus 6 all over x plus 2. Then we combine like terms in the numerator. We get 2x squared plus x minus 6 over x plus 2. And when we factor 2x squared plus x minus 6, we get 2x minus 3 times x plus 2 all over x plus 2. And then the x plus 2's cancel. And we end up with 2x minus 3. Okay, once again, you cannot forget that the subtraction has taken place here, and that you have to subtract the whole numerator. Now, let's find the LCD. To find the LCD, you factor each denominator completely. Okay, that's the first step. The least common denominator is the product of all unique factors found in step 1, raised to the power equal to the greatest number of times that the factor appears in any one of the factor denominators. That may not make sense to you, but let's just recall a simple example of finding the LCD, and we'll get to explaining this step 2 down here. Now look at 8 over 3 and 2 over 5. When we find the LCD, we're finding the smallest multiple of each of those denominators. Okay, we're finding the smallest number that is a multiple of both of them. And in the case of 3 and 5, it's pretty easy to see that the smallest number that's a multiple of both of them is 15. So we found the LCD of 15 for both of these. Now, let's see what happens if we put to use the steps that were just given to us. So it said, factor each one. So if you remember, the prime factorization, this is exactly what they're talking about, prime factorization of numbers. So if you have a 9, 9 is factored into 3 times 3, which is 3 squared. We always want to write it with the exponential expression here. 15 and its prime factorization is 3 times 5. Okay, so there are no squares there. Now what this part 2 step was saying was, find the LCD has to contain all of the unique factors that appear in any one of these prime factorizations, but we want the one that appears the most. We want the one with the biggest exponent. So let me tell you what I do. Look at these prime factorizations here. 3 squared and then 3 times 5. What different factors do you see here? So 9 has 2 factors of 3. 2 factors of 3. 15 has 1 factor of 3 and 1 factor of 5. So what my LCD has to contain is it has to contain some 3s and some 5s, because those are the only different factors that appear in either one of these two. Okay, there are no 7s or 11s or 2s or anything else here that are prime numbers, only 3s and 5s. The thing is, I want the 3 and the 5 that have the biggest exponent. So the 3 squared has a bigger exponent than just the 3 down there with the 15. So that's the exponent I want to take. I want to take the 3 to the second power because that's the biggest exponent. The 5 only has 1 as an exponent, so we keep 5 the way it is. And once we have figured out what each different factor we see and the biggest number of times that it appears, this will be our LCD. So we have 3 squared times 5, which is simply going to be 45. Okay? Now, let's do it again with 2 terms here that have variables as well. Now remember, the LCD is going to be the factor with the largest exponent. Okay? Largest exponent on that prime factor. So we have 6 x to the third and 8x to the fifth. Well, the 6 really factors to 2 times 3, and x to the third is just x to the third. The 8 factors to 2 to the third power times x to the fifth. So the LCD has to contain some 2's, some 3's, and some x's. Now, how many 2's does it have to contain? It has to contain the 2 with the biggest exponent, so that's going to be 2 to the third. It has to contain the 3 to the biggest exponent, well, that's just the 3. And it has to contain an x to the biggest exponent, which is x to the fifth. So we have now the LCD is going to be 2 to the third times 3, so that's 8 times 3, which is 24. X to the fifth. Okay, we're finding the LCD. If the if the denominators cannot be factored, in other words, if they are prime already, then the LCD has to be the product of the two. Just look at these two right here. A plus 5 and A minus 5. They cannot be factored. We had an earlier problem. I can't remember exactly what it was, but I might have had 3 over 5 and 2 over 3. Look at 5 and 3 as the denominators. They cannot be factored. They're both prime. So the LCD is going to be the product of those two. It has to include a 5 and a 3, a 5 and a 3, which we know is 15. So it has to be the product of the two. Same thing with this other one at the top here. 3a over a plus 5 and 7a over a minus 5. The LCD has to contain an a plus 5 in parentheses times an a minus 5 in parentheses. If the denominators cannot be factored, then the LCD is going to be the product of the denominators. So in this case, negative 2 over y and 5y over y minus 3, the LCD is going to be what? Well, y cannot be factored, so the LCD has to contain a y. Y minus 3 cannot be factored, so the LCD has to contain a y minus 3. And that's it. Now, we have to factor to find out the LCD. Well, this particular denominator is factored already. Okay, it's already factored. X minus 4 squared means x minus 4 times x minus 4. But this one is not, the other one is not, so let's factor it. We have 3 times x minus 4. So we factored it. So now we identify every unique, that means different factor that we have. We have some factors of x minus 4. We have it here and here. Okay. And we have factors of 3. A factor of 3. So our LCD must contain a 3, and it must contain an x minus 4, and it must contain x minus 4 to the biggest exponent, which is the second power. Okay, so the first denominator here, we're going to find the LCD here. The first denominator is already factored. The second one must be factored. We're going to factor out a 3, and it leaves us a 2x minus 1. So the LCD must contain a 3 and a 2x minus 1 to the biggest exponent would be squared. Okay, remember to find the LCD, you factor if you can. Factor the denominator. So here we have y and y. Then we need two numbers to multiply the negative 3, but add to a positive 2. So it's going to be a plus 3 minus 1. Then over here on the other one, we factor y and y. Then we need two numbers to multiply to a positive 2 and add to a negative 3. So that's going to be a negative 2 and a negative 1. All right. So the LCD must contain, let's see what we have different here. We have a y plus 3. We have y minus 1. We have y minus 2. Okay, and we have another y minus 1, but we only included, when we were first writing it, let's write it one time. Here we have y plus 3. We have to include. We have to include a y minus 1, and we have to include a y minus 2. Now, the y minus 1, we do not include it 2 times because the only exponent, now watch what I'm putting here. I'm putting an exponent of 1 right here and 1 right here. We only include it more than one time if it appears more than one time in any one of these denominators. So it doesn't appear more than one time here in the first denominator, and it doesn't appear more than one time in the second denominator. So we only include it once in our LCD. Let's find the LCD of this one. Now, look at these two expressions here. We have 5 over 3 minus x and 4 over x minus 3. Now, look at these two. They're not the same, but they are exact opposites of each other. In the first one, the 3 is positive, and the second one, the 3 is negative. In the first one, the x is negative, and the second one, the x is positive. So they are exact opposites of each other. Now, what you can do, and what you have to do, is really factor out a negative 1 from one of them. So let's say if I look at this first one, and I factor out a negative 1. then what do I get? Well, I get a negative 3 plus x, right? Negative 1, I factored it out, and it changes the sign of each of those terms. But look at what I can do now. Using the commutative property, I can rewrite this as positive x minus 3. Okay, so notice now we have x minus 3 in both of these denominators now. Okay, so my LCD has to now include a negative 1 from this first factored binomial, and it must include an x minus 3. Okay, that's it. Now, we want to talk about writing equivalent rational expressions. All of this is in the same section. Remember, fractions can be written in multiple ways. I mean, for instance, if I give you 75 over 100, 75 over 100, we know that reduces to 3/4. But that's not the only way to write 3/4. We can write 3/4 as 9 over 12. There's an infinite number of ways of writing 3/4. Well, there's an infinite number of ways of writing 2/3 as well. Now look at this one. First example here. I want to write 2/3, but I want to write it with a denominator of 15. So I want to change it. I'm building up. We're doing basically the opposite of reducing fractions. We're kind of building them up. So I want to write a fraction that's equivalent to 2/3, but has a 15 as its denominator. Okay, and so what I do is I ask myself, what is it? What factor is missing between, look at the denominator. 3 is multiplied by what to give you a 15? 3 is multiplied by 5, right, to give you 15. So 2 has to be multiplied by 5 as well if I'm going to maintain the equivalence of the fraction. So that's what we're looking for. I'm looking for the new numerator that's going to create an equivalent fraction. So what will the new numerator be for the second one? 11 over 12 equals what over 48? What's the missing factor of 12? 12 times what? 4, right? And then 11 times 4 has to be multiplied by 4, so it's going to be 44 over 48. We're building them up. We're doing the opposite of reducing. We have to know how to do this in order to get to the point where we can add fractions that have different denominators. Okay, so for 9a to become a 27a squared b, what's going to be the missing factor? Well, let's see. We need to multiply 9 times, 3. We need another factor of a, and we need a factor of b. So we need to multiply 9a times 3ab to make it look like 27a squared b. But the numerator's got to be multiplied by that too, 3ab. So we get 12ab squared. Okay? Well, then we have 5y. 5y, to make it look like 20x squared y squared, must be multiplied by a 4x squared y. Okay, so I'm going to multiply by 4x squared y in the numerator. So it gives us now 28 x to the third y in the numerator. We are writing equivalent rational expressions. Now, for this one, we have to make sure we can't really see what we have to multiply by unless we factor our denominator as much as possible. Well, 3y squared, y plus 2 can't be factored. But 15y plus 10 can be, so we factor out a 5, and we have 3y plus 2. Now it's easy to see what's missing from here that you have over here. It's a factor of 5, so 3y plus 2 has to be multiplied by 5, which means 11y has to be multiplied by 5. Do you see that? Where it's missing, if I want to make it match, I have to multiply by 5. So that gives us 55y. Okay, look at the next one. 4x plus 7 cannot be factored. There's no common factor in 4x plus 7, but 8x plus 14 has a 2 in common, and so that gives us a 4x plus 7. 2 times 4x plus 7. Now the missing factor is 2. So that has to be multiplied by 2. And so there's the 9x. So we have 18x. Okay? All right, now we have to see what the missing factor is so we can multiply it. We are writing equivalent fractions, so we have to factor now. We have to factor this one in order to see what's going to make it match over here. So we get x and x. We need a plus and a minus because then 15 is negative. So I need two numbers that multiply to negative 15 but add to negative 2. So that's going to be a negative 5, positive 3. Now we can look at this and this to see what's missing. What's missing is a factor of x minus 2. So if we multiply this by x minus 2, we have to multiply this by x minus 2. All right, and let's multiply it. We get 3x minus 6. That's the new numerator. Okay, one more. Let's factor. X squared minus 25 is a difference of 2 squares. So we're going to go x plus 5 and x minus 5 multiplied times each other. So what's the missing factor? What's going to make it look like that? We are missing in what x minus 3. So that's what's missing. That's what we have to multiply by here, x minus 3 in the numerator, to give us a 3x minus 9 as our new numerator. Now you have to go and practice these because we're going to use these concepts in the next section where we're adding fractions with different denominators.